We move now to randomized testing of Byzantine fault-tolerant algorithms. Levin will be presenting this work, which, as you can see on the slide, is one of the distinguished papers.
Yeah, thank you for the introduction. My name is Levin Winter, and I'm going to present our research paper on randomized testing of Byzantine fault-tolerant consensus algorithms. This is joint work with Florena, Daan, Klaus, and Burcu. As you probably know, in recent years, blockchains have increasingly increased in popularity. These systems often run on a set of distributed validators, which all keep a local history of the transaction and the blockchain. When a new transaction is submitted to the network, these validators need to agree on the order of these transactions. For this, they typically use Byzantine fault-tolerant, or BFT, consensus algorithms. In our work, we focus on consortium-based BFT algorithms, which are much like the seminal PBFT and its variants. Unlike crash fault-tolerant consensus algorithms, so for example Paxos or Raft, Byzantine fault-tolerant consensus algorithms are resilient to malicious, or also called Byzantine nodes. To better understand what that means, let's have a look at an example. Below, you can see the execution of Ripple's XRP ledger consensus protocol, and I show you the messages that the 7 validators that we have in the system exchange throughout time, where time flows from left to right. In general, these consensus protocols are structured into rounds, and as you can see here, we have 5 distinct rounds. 1 transaction round, and then 2 proposal and validation rounds, which alternate. During the transaction round, P3 disseminates a transaction that it received from a client to all of its other peers, and we denote this with the blue arrows. This is followed by a proposal round where all of the validators share their intent to include this blue transaction into the next ledger I. Once the validator sees sufficient agreement with all of its peers, it moves on to the validation round. Here, it casts its final vote on wanting to include the blue transaction into ledger I, and once it reaches a quorum with all of the other validators, it will commit this blue transaction to the log. Since no new transaction has been submitted to the network, in the following proposal and validation round, they agreed to not include any transaction into ledger I+1. So far, so good. But as you know, not everything always goes according to plan. So let's imagine that P1 crashes during the 3rd round. It's not able to send any validation or proposal message afterwards anymore. As you can see in the chart, the rest of the cluster is able to continue normally because the protocol is resilient to crash faults. Since this is a Byzantine fault-tolerant consensus algorithm, it is also resilient to Byzantine faults. So let's imagine that P6 turns evil and sends a malicious validation. Then you can see again that the rest of the cluster, all of the honest nodes, continue to correctly operate, and the protocol makes progress. I think you can all imagine that in order to deliver these guarantees, it is essential that the protocol is implemented correctly. Unfortunately, this can be quite difficult in practice, as these systems often become very complex. And even BFT algorithms whose models have been formally verified can have buggy implementations. What I just described is not just a theoretical concern, but an actual issue in practice. Over the years, many adversarial scenarios have been detected in several BFT systems and their preliminary versions. We therefore identified a strong need for testing tools for BFT algorithms. Unfortunately, in general, the existing testing methods do not sufficiently address this Byzantine behavior. Byzantine behavior is defined to be arbitrary and unbounded in nature. This means that basically anything is possible except a few limiting constraints, like Byzantine validators cannot break cryptography. I think that makes sense. Unfortunately, the existing tools do not sufficiently address and explore these Byzantine behaviors. We therefore set out the goal of designing a testing algorithm for distributed systems that can detect these BFT bugs while remaining practical and applicable to large-scale blockchains. Our response to this goal is ByzzFuzz, a randomized testing method for BFT algorithms. It relies on 4 key insights. The first is that we bound the number of faults that we inject into the system in order to ensure that it continues to make progress. Secondly, we simulate network partitions, as these have been shown in the past to expose some of the bugs. Third, we use structure-aware mutations. This is inspired by the input generation from traditional fuzzing, and it means that we preserve the general structure of the message in order to make it remain correct. Lastly, we propose the new concept of small-scope mutations. These small-scope mutations apply a small change to a value. We hypothesize that this is sufficient to expose most of the bugs in a distributed system. A small change can either be small in absolute value, meaning that you, for example, increment or decrement an integer, or it can be small in temporal difference, meaning that you replace a hash with, for example, a hash that has been previously in the network. We hypothesize this because we think that these small changes expose most of the bugs. We used ByzzFuzz to discover previously unknown bugs in several blockchains. To better understand how we did this, let's have a look at an overview of ByzzFuzz. The developer supplies as input a list of processes procs and 4 integer parameters. ByzzFuzz then continues to randomly select F processes to be faulty. It selects D rounds during which a network partition will be applied, and C rounds during which we apply our structure-aware and small-scope mutations to the messages that are in flight. These faults are distributed among R rounds of the consensus algorithm. Once this is done, ByzzFuzz can start the execution of the protocol. We mutate or drop the messages that are sent between the different processes according to the previously generated fault configuration. For this, we use a given set of message mutations that has been supplied. After the execution completes, we check for the 4 consensus properties of agreement, integrity, validity, and bounded termination. Okay, I think to better understand this, let's have a look at a concrete example. Here you can see how ByzzFuzz, or well, now you can't see it, but I will show you how ByzzFuzz injects 1 process fault into the execution of Ripple's XRP ledger consensus protocol. We again have the 7 validators, and ByzzFuzz randomly selects that P3 is going to be the Byzantine validator. We instruct ByzzFuzz to distribute the process fault among one of the 5 rounds that we've already seen. ByzzFuzz then randomly determines that during the 3rd round, so the first validation round, the validation messages sent from P3 to P1, 2, and 4 will be mutated. We're now ready to start the execution of the protocol. We again have the transaction round where the transaction gets disseminated, and the proposal round where all of the validators agree to or propose to include the blue transaction into ledger I. We've already seen this. Now comes the interesting part. Okay, the slides are back. Cool. I guess the slides got too excited. I don't know. Okay, now comes the interesting part. All of the correct validators propose to validate ledger. This really caught me off guard. Okay, all of the correct validators send a validation message for ledger I, whereas ByzzFuzz. Okay, let me try this again. All of the correct validators send a validation for ledger I. You can see that at the top. ByzzFuzz now mutates, I don't know. I keep seeing the slides over there, so yeah, I don't know what that is. But ByzzFuzz mutates the validation that is being sent from P3 to P1, 2, and 4 to be a validation for ledger I+1. This happens in flight, and this mutation is a structure-preserving and small-scope mutation because it slightly changes one of the messages fields. The execution of the protocol continues, and so far everything seems to happen normally. All of the validators propose to not include the transaction. But during the validation round, you can see that the consequences of the mutated validation message manifest. All of the validators that previously received this mutated validation are not able to themselves send validations anymore. This is because their internal state got corrupted, and they cannot send validations anymore. Because there are not sufficiently many validations in the network, they cannot reach a quorum and therefore cannot make progress. This violates the consensus property of termination. We have just found a buggy execution. This is actually a bug that ByzzFuzz detected in the production implementation of the XRP ledger that was previously unknown. I would like to highlight that this bug only exposes using our small scope mutations because the ledger sequence numbers are checked to be in a specific interval. In our endeavor to thoroughly test ByzzFuzz, we applied it to 3 blockchains. For an implementation of PBFT, we detected a known liveness violation and 3 implementation bugs. For the production implementation of Tendermint, we discovered 1 potential liveness vulnerability. However, our most exciting results were, as you can probably already think, with the XRP ledger. Here, we discovered 2 known protocol vulnerabilities and 1 new variant of these, as well as, most noteworthy, this new implementation bug that was previously unknown in the reference implementation of the XRP ledger. Let's have a closer look at these results just to get some more insights. On the left, you can see the configuration of ByzzFuzz. So C is the number of process faults that we inject, and D the number of network faults. In the subsequent columns, you can see how many out of the 300 configurations, out of the 300 executions that we ran per configuration, violated one of the 4 consensus properties of termination, validity, integrity, and agreement. In addition, for every configuration that had at least 1 process fault, we ran 1 set of experiments using our small scope mutation and 1 set of experiments using the any scope mutations. Any scope mutations don't make a slight change to the value, but replace it with an arbitrary one, so a randomly generated one. Furthermore, we implemented a baseline fuzzer that randomly flips bits and randomly drops messages. As you can see, this baseline detected significantly fewer buggy executions and only managed to expose 1 of the several bugs that ByzzFuzz found. I would also again like to draw your attention to the second last column, where you can see that some of the bugs only expose using our small scope mutations and not using any scope mutations. Much like the bug that we've already seen, there were also other bugs that also only exposed using our small scope mutations. But this bug that I just showed to you in the previous example existed because the developers ignored the fact that there are malicious nodes, or there could be malicious nodes in the network when implementing a particular part of the system. They assumed that incoming validation messages are correct, coherent, and as we know, this doesn't always have to be the case. We have reported this bug to Ripple, and together with them, I developed a fix which since has been merged into the production branch. And I would like to highlight that our bug was deemed eligible for reward under Ripple's bug bounty program. To conclude, I've shown you ByzzFuzz, which, to the best of our knowledge, is the first randomized testing tool for Byzantine fault-tolerant algorithms that found actual BFT bugs in production blockchain systems. It relies on the 4 key insights of bounding the number of faults in order to ensure progress, of simulating network partitions because they can often expose buggy scenarios, and it uses the structure-aware and small-scope mutations, where, I place an additional emphasis on the small-scope mutations. We use ByzzFuzz to detect previously unknown bugs in several production blockchain systems, and if you have any questions, I encourage you to have a look at the paper, ask now, or talk to me after the conference. Thank you very much.
Good timing. Please.
Thanks for the nice talk. I have a question about, like in your test, how many participants do you use? Like in your example, you mentioned it's 7 participants, but in your experiment, maybe you use more than that, or you think just using 4 participants, or just not 7 participants are just enough?
So in the experiments for the XOP ledger, we indeed used the 7 participants. I'm not entirely sure about the PBFT experiment and Tendermint, but yeah, we always kept that constant and just simulated a smaller network. Yeah.
Okay, so like, is it like guaranteed that like if there's no problem with the 7 participants, then there's no problem with more participants?
No, I mean, that is not guaranteed, but so this is a randomized testing method, so I mean, there are really no guarantees to this method, but yeah, we decided on this configuration because, yeah, it was quite approachable, it made sense for us, but yeah, you could, of course, you could apply this method to a larger cluster if you wanted to, so you could sample more faulty processes, increase the general number of validators, so these are definitely things you could look into if you wanted to.
Yeah, thank you for...
Yeah, thanks.
Hi, thank you. It was a great talk. I was wondering how easy or how difficult it is to apply this technique, the system, to other blockchains. I mean, there are different consensus protocols, there's different implementations, and like, you know, do you have like maybe like plans to do it, or maybe instructions on how other, you know, blockchains could take advantage of that?
Yeah, so I think I can really answer that question because, for example, for the XRP ledger, there we implemented this system from scratch. So what you basically need is a message interception layer. We basically implemented a giant proxy through which all of the messages are routed. And if you have such a message interception layer, you just need to implement the ByzzFuzz algorithm, which really is very simple, so that shouldn't be much of an effort. But yeah, you need to have control over the network and be able to mutate the messages. But if you have that, yeah, you're set and you can use ByzzFuzz.
Thank you so much. Thank you.
Yeah, thanks.
So I have also a question. The mutation seems very specific to the use case. Are you exploring to see if you could use it for other kinds of distributed system algorithms?
So you mean this increment of that sequence number? It's now very specific.
It is, yeah.
Yeah. So I mean, this is something where the developer would come in and not guess, but use their judgment to make up these mutations. But of course, this is also something that you could try to automate. So in our future work, we want to look at more intelligent ways to devise these mutations to better ingest these faults. So this is something we plan on doing.
Okay, thank you, Levin.
Yeah, thanks.